Late last night, something extraordinary and controversial unfolded deep beneath the French-Swiss border. Official CERN data logs confirm that the Large Hadron Collider, the world's most powerful particle accelerator, surged nearly 12% above its published safety threshold. Moments later, anomalies lit up detectors across multiple sectors, triggering emergency safety protocols and an avalanche of debate across the scientific world. What happened wasn't just another calibration glitch. According to internal notes, researchers observed unusual magnetic fluctuations, erratic beam losses, and what some described as a portal-like effect. Now, to be clear, there's no solid evidence of an actual portal or dimensional rift. But the data patterns were unlike anything ever logged before. So what really happened inside CERN that night? Was this a hardware malfunction, a routine anomaly, or could it be the first glimpse of physics beyond the standard model? Every system in the Large Hadron Collider, from its superconducting magnets to the vacuum beam pipes, operates within limits designed to stay far below the actual danger point. If a magnet can handle 8.33 Tesla, CERN doesn't run it at 8.33. They run it lower, perhaps 7.9 or 8.0, to leave a buffer zone. These margins are based on years of experiments, simulations, and safety testing. So when a reading shows the collider went 12% beyond the safety threshold, it raises alarms not only among engineers but also physicists around the world. It constantly monitors thousands of parameters: temperatures, currents, beam positions, and magnetic fields. If even one sensor detects something abnormal, it sends a signal within microseconds, triggering a chain reaction that can shut down parts of the collider instantly. Meanwhile, the beam interlock system works like a security gate. It won't let a single particle beam circulate unless every subsystem, from cryogenics to power converters, reports that it's safe. If just one valve, one pump, or one magnet isn't in perfect condition, the interlock blocks the experiment entirely. In theory, no single failure should ever bring down the collider. Around 11:42 p.m. Geneva time, monitors at sector 6 to 7 showed an unexpected spike in beam current and magnetic field intensity. Seconds later, detector logs began showing strange patterns of particle tracks, some forming symmetrical spirals, others curving as if influenced by unseen magnetic fields. According to a leaked internal report, the data resembled interference patterns consistent with field overlap, a term often used when two energy domains interact in ways standard models can't fully explain. The LHC's automatic protection system reacted instantly. A full beam dump was triggered, safely ejecting the remaining protons into massive graphite blocks designed to absorb their energy. Some appeared to bend against expected magnetic gradients, as though affected by a force outside standard electrodynamics. Others simply blinked out mid-flight, leaving partial tracks, like unfinished trails through spacetime. It came from CERN's own technical incident notes, where a researcher described the data as resembling a field resonance, producing localized energy distortions with overlapping phase domains. That's science speak for what, to an untrained eye, might look like a portal, or a temporary spatial overlap between dimensions. It refers to a hypothetical interaction channel between the known universe and hidden sectors, the kind predicted by models of dark matter or extra dimensions. So while no glowing doorway appeared under Geneva, it's possible CERN's data showed momentary evidence of a new interaction, something that standard quantum field equations can't yet explain. Officially, CERN has not confirmed any new discovery. Their public statement describes the event as an unexpected but controlled operational anomaly under investigation. Unofficially, insiders admit the surge forced an immediate safety review, temporarily halting several runs. Because even if this was just a control system fault, the data recorded before the beam dump is unlike anything seen since the Higgs boson detection in 2012. Dr. Amelia Kreutz, a theoretical physicist not affiliated with CERN, commented that the readings hint at exotic particle behavior possibly tied to hidden symmetry breaking or quantum vacuum fluctuations. In simpler terms, something weird happened, and it may not be a glitch. Let's zoom out for a moment. For years, physicists have been searching for signs of physics beyond the standard model, evidence that could explain dark matter, dark energy, or the unseen structure holding the universe together. The LHC has already discovered the Higgs boson, but since then, progress has slowed. So if even a tiny fragment of this new data holds up under analysis, it could reignite the next era of particle physics or even confirm theories once dismissed as science fiction. Rumors of portals, time shifts, or mini black holes have haunted the collider since day one. Yet behind all that drama lies a deeper truth. The Large Hadron Collider is humanity's most ambitious experiment, a machine designed not to destroy, but to understand the invisible threads that hold the cosmos together. Right now, CERN's analysts are combing through terabytes of raw data from that night. They'll cross-check every spike, every fluctuation, and every detector event. If it turns out to be a measurement error, safety protocols will be updated. But if even one of those anomalies resists explanation, we might be looking at the first evidence of a new physics frontier, something that could reshape our understanding of matter, energy, and reality itself. As one CERN engineer reportedly said, "We didn't open a portal. But we might have opened a question we're not yet ready to answer." Whether this surge was a harmless anomaly or the start of something revolutionary, one thing is certain: CERN just reminded the world how close we stand to the edge of the unknown. And maybe, just maybe, that's where the next great discovery is waiting. Thank you for watching my channel.